All right, last time we started section 6.3, and we took a look at the first part, which was multiplication of rational numbers. And today we're going to finish up with the other part, which is the division of rational numbers. And we're going to jump right back in to a definition of division. So, if A over B and C over D are rational numbers, and we divide them, and the answer is E over F, then that will only work if E over F is the unique rational number that would have multiplied by C over D to give you A over B. For those of you who have seen our book's definition of division, either in whole numbers or in integers, this looks very similar. I'm just going to use an integer example, whole number example, so you can see what I'm thinking about when I'm writing it. Basically, it's saying that if 6 divided by 2 equals 3, then the only reason and way that that is true is if 2 times 3 is equal to 6. So a lot of times you'll see the phrase fact family used when you talk about this relationship. So there's this similar relationship backwards if we have the ability to do division. And we do have the ability to do division, except when zeros unfortunately get started to being involved with these kinds of things. There's a very interesting algorithm that you probably remember for division of fractions. So if A over B and C over D are rational numbers, and C over D is not 0, then A over B divided by C over D is equal to A over B times D over C. So you might have heard it say, there's all, I can't even remember them now because I've seen so many middle school teachers teach and seeing acronyms used in these sorts of things in the 6th and 7th grade. What do they say? And I'll hear that used with negatives as well, like that. So the basic idea is that division turns into multiplication by the reciprocal, right? I mean, that's what you're doing. You're flipping the fraction at the end, and it becomes multiplication. But I'd like for you to understand why that works, because it looks a little bit like magic. And there's a really very good reason why it works. So we're going to actually show why that's working for us, because undoubtedly somebody in here is going to teach this and have some kid in the class who maybe really wants to know, or who maybe is just trying to be, a little bit smart alecky, and they want to know why it works, and you'll have an answer, or at least you'll be able to go find an answer because you know one exists. So we're going to start with A over B divided by C over D, just like it starts with on the left-hand side of the equation that I sort of gave you. And what I'd like to do is I'd like to rewrite it as a compound or a complex fraction. So in other words, I'd like to write it as A over B over C over D. Right? That's another way of writing that division sign, correct? It's fraction. So if I don't want the double fraction involved, I know I should and can multiply by the same thing on the denominator, the big denominator, as I do the big numerator. So if I multiply my big denominator by D over C and my big numerator by D over C, what we see happen here is that these cancel, right? I get a denominator of 1. So I end up with A over B times D over C over 1, which means I just have A over B times D over C. And all I did to get there was to rewrite it in a different form and then to simplify the fractions that existed. All right, I mentioned when we talked about multiplication that multiplication with fractions can be really hard for students because it's perhaps the first time they've multiplied where they multiply and things don't get bigger. They might actually get smaller. In fact, many times do when they're multiplying by fractions. And division has the same sort of a problem. Most of the times, prior to working with fractions, students think division makes things smaller. I'm dividing things up, right? So they're getting smaller. And so if you talk about 6 divided by 2, there's two different ways to talk about division. So I want to show you what both of them are. One way is to talk about taking 6 items and putting them in 2 groups. Hence, the groups are smaller than the original number of items. And so when you think about your items, here are 6 items, and we split them in half and we make 2 groups. Now, that doesn't work very well for extending into the idea of fractions. So if I say, okay, well, let's do 6 divided by 1/2. So I make 1/2 a group. Like, it's weird, right? Because I can't make a 1/2 group. I mean, the language doesn't even work very well for that description. So the second option is that we could describe it this way. We have 6 items, and we want them in groups, of size 2. So I have my same 6 items. The answer, of course, is going to be the same. The question that we would be sort of looking for in the first question is how many items are in each group. If I split them into groups of size 2, the question would be how many groups do I have, right? And it would be 3. So here there are 3 groups, and up here we end up with groups of size 3 in each group. The second description works for fractions. So we're going to take an example of 6 1/2 to see how it works. So again, I have 6 items. And instead of groups of size 2, I'm going to make groups of size 1/2. Well, I can do that. Imagine that they're cookies, right? What would I do? I would just cut the cookies in half, right? So there are 12 groups of size 1/2. You guys have probably all had something like this happen before, where either more or fewer people showed up to a birthday party and you decide based on how many people are there, how many slices to cut the cake into, right? Yeah. So we just simply make the groups, whatever they are, of size 1/2. Obviously, there's certain contexts that this doesn't work. We can't half a person. It's not appropriate. I know, right? So we do have to be sort of aware of the context that we're using this. But this does give us a pretty clear sort of picture as to why I take 6 and I divide by 1/2 and it gets bigger. I have more groups. They're smaller size, though. I mean, there's a smaller aspect to this, obviously. But I do end up with a bigger number when I'm done. I can feed 12 people with those 6 cookies now because I cut them in half. Okay? It also shows why this ends up becoming the same as 6 times 2 over 1, right? Because I also end up, visually speaking, with 12 items, which is the same as 6 times 2. All right. A little foray into some exponents. For rational numbers a and a rational number n, a to the n is a times a times a n times. Our book talks about definitions, or not definitions, but properties of exponents in 2 different chapters in the book. One of them occurs in number theory. So if some of you are looking at this and feeling like I've shown you this before, you're right. And if you haven't seen this before, you'll see it again in number theory when you take that course. So the first 4 show up in number theory. The last 2 are new as they apply specifically to chapter 6 now. So can anybody help me and remember, what is a to the m times a to the n? How does that simplify? Right. We add exponents, and I'm going to talk more in a minute about why that's the case, in case you haven't seen it or haven't seen it recently. The second one, a to the m over a to the n. Yep, we subtract exponents. How about the third one where I have a to the m to the n? Yep. Y'all know Brooke took that class last semester, right? So she's sort of kind of cheating, but I'm grateful. Yeah, we're going to multiply the exponents, a to the m, n. On number 4, ab to the m. Yeah, it feels like distribution, right? And I think 5 was our last one that we did back. No, we didn't have 5 because we didn't have fractions. It works the same way on number 5 as it did on number 4. We're doing that distribution kind of a feature. We're just doing it across a fraction. A to the m over b to the m. Number 6 is interesting. It looks a lot like 5. It's just got a negative exponent instead of a positive exponent. So not only does it distribute, but it also flips it to make the negative sign not negative. So anytime we raise something to a negative, again, I'm going to explain more why this works in a minute, but anytime we raise something to a negative, it flips fractions upside down. So this actually becomes b to the m over a to the m. All right, so we're going to do some examples, but I'm going to do examples that show the explanation for why things work. That's what I'm going to do next. So I want to talk about why in the world it's actually true, and I'm going to show it to you by way of a concrete example in each case. So we just said a moment ago that this is a to the m plus n, and the example I'd like to show you is what happens when I have a to the third times a to the fourth. So what does a to the third mean? Right, we would multiply a 3 times, and a to the fourth means I would multiply it 4 times, right? So I have 3 a's followed by 4 a's, which gives me a total of how many a's? 7. So this is a to the 7th by definition. And how do we get from 3 and 4 to 7? Well, we add. And that's a concrete example of why that has to work that way. On this one, this was a to the m minus n. So we're going to do, for example, a to the 5th over a squared. So the a to the 5th is 5 a's. A squared is 2 a's. And when we have variables, of course, written side by side, we mean that they are multiplied, whether we have the dot or not. And so because these are all multiplied together, I am able to reduce, which is what a lot of our incorrectly thinking students have been doing, like John in the problem, right, Hannah? Yeah. Okay, so I can reduce from the numerator to the denominator because they're factors. And if I do that, I end up with a, which is, of course, a cubed. And how do I get from 5 and 2 to 3? Well, I subtract. All right, so our next one said that we were going to multiply like so. So to use as an example, I'm going to use that a cubed, and we're going to square it. So as you know, a cubed means a, and the fact that it's squared means that a is there twice. So how many a's do I have? 6. And how do I get from 3 and 2 to 6? I multiply. We said this one was a to the m, b to the m. So we'll do cubed, ab cubed. So this means ab, ab, ab. And then because multiplication is commutative, commutative means you can change the order, right? 5 times 3 is 3 times 5. And because it's associative, which means that I can regroup things, I can use both of those properties to regroup all the a's together at the front and all the b's together at the back, so that I see a cubed, b cubed. Number 5 is similar, maybe even a bit easier to see, just because there's not the regrouping necessary. So again, we said that it's a to the m over b to the m. So if I have a over b cubed, then I'd have a over b times a over b times a over b, which is a over b, or a cubed over b cubed. Okay. The last one may be the weirdest because we have two things going on. We have this reciprocal business going on, and we have our distribution going on. So on this one, I have a over b, and I'm going to do it as the -3. And I'd like for you to recognize that -3 is the same thing as 3 times -1. So I'm simply going to separate this to be to the 3 and then to the -1, which is really using property number 4 backwards. I'm undistributing something. Or not property 4, property 3 backwards. Property 3 said that I can multiply the two exponents that are raised to the power a raised to those powers. And this was saying, okay, well, if I can multiply them, I can separate them too. So we know what happens with the a cubed b cubed because we just did it. Right? That was the property number 5. And then this -1 actually has a meaning. -1 means multiplicative inverse. And a multiplicative inverse is another word for reciprocal. So I'm going to take the reciprocal, which means I now have b cubed over a cubed. Okay, I have 2 additional exponent facts that are kind of some fun ones that are interesting to show. Does anybody remember what a to the 0 is? It's 1, and I'm going to prove it in here in a second. How about a to the -n? Yeah, 1 over a to the n, like that. Okay, so let me show you why a to the 0 is 1, excuse me, because it's kind of an interesting one. So we're going to start out with a to the 0, and we're going to recognize that that's the same thing as a to the m minus m, right? M minus m is the same as 0. But if I use property number 2 in the sort of reverse order, this is the same as a to the m over a to the m, right? But what happens when you divide a to the m by itself? You get 1. And all we're doing is using the properties we already had to prove that. It's a legit proof, actually, because I didn't even use numbers where the m's were. I did it very generically. All right, let's take a look at the next one, the 1 over a to the n. I'm going to do this one with an example for numbers, though. The last one I didn't do. This is actually a proof. You can tell somebody you proved something in math today, okay? All right, we're going to use an example for this one, though, so I'm going to use a to the -3. So again, we can separate it much like I separated the last one, where I have a to the negative 1 to the 3, or you could do it the other order, but I'm going to go with this order on this one. So a to the negative 1 means what's the reciprocal or the multiplicative inverse of a, and that's 1 over a. And now it's to the power 3. And then using property 5, I have 1 cubed over a cubed. Of course, 1 cubed is 1. So I end up with a negative 1, or a positive 1 on top with the positive a cubed version on bottom. Okay, so every time I teach this, somebody thinks that I'm intending for you to sort of draw out all your problems and prove everything again. I'm not. I want you to be able to use the properties, but I want you to know that it's not just like somebody created them somewhere and there's no real like backbone behind them. They're all provable facts. I've given you some concrete numeral examples on most of them to say why they should work that way, and they do work that way all the time. Now that you have facts 1 through 8, for lack of better numbers, the way I've numbered them, you're going to use them that way, okay? You're going to use the simplified facts that you know to clean up and simplify other messes, for lack of better terms here. They're messes, right? So we're going to do example number 6, which is to write in simplest form with positive exponents. There's lots of ways to do these problems. So if I do a different way than you do, we both end up at the same point at the end. Chances are pretty good that we're both doing the right things. Okay, it doesn't always work, right? Like our 16 guy over 64. But usually that's the case. So there's definitely more than one way to do this problem. So I'm going to try to identify for you which of the properties I'm using as I'm using them. For example, on this first one, I have a numerator and I have a denominator. I'm going to start with property number 2, because property number 2 told me what happens when I have a to a power in the numerator and a to a power in the denominator. I can subtract them. So this is actually the same as a to the 1 minus negative 3 and b to the 4 minus 2. Again, not the only way I can do this problem, but it's an option. What happens when we subtract a negative? What is 1 minus negative 3? Yeah, it's 4. We add. This is a to the 4th. And what about b to the 4 minus 2? B squared. If I ended up with anything negative, like exponents that were negative at that point, I'd have to take one more step to pull those negatives back to the denominator, those negative exponents back to the denominator. Okay, on part B, what I want to drive home to you is all of the properties we did 1 through 8 all hinged on the bases being the same. And 2/5 and 4/25 are not the same, right? So I can't just jump in and use any of those properties at all right now because they don't have the same base. It's kind of like on the first problem, I couldn't combine the A's and the B's together. They're not the same. I can't do that either with the 2/5 and the 4/25. But I can try to make them the same. So 2/5, that's kind of as simple as it gets. But 4 and 25 are both numbers that factor, right? So let's try and simplify what we have to see what we can do next. So the 2/5 to the 3rd is all good. But 4 over 25, let me just kind of make an aside over here. If I factored it, I'd get 2 times 2 and 5 times 5, right? Well, doesn't that look an awful lot like what would happen if I took 2/5 times 2/5? Well, yeah. But what's another way to express a number multiplied by itself?
Squared.
Right. Squared. So down here in the problem, instead of having 4 over 25, I can have 2 over 5 squared to the -6. And now they both have the same base, 2 over 5. So as I'm working on that, I'll multiply that 2 and that -6. So this is now 2/5 to the -12. How can I combine the 3 and the -12? I would add them. So this would now be 2/5 to the -9th. The fact that it's negative means I need to do what? I need to do the reciprocal. I need to flip my fraction. So this is 5/2 now to the +9. And you can leave it right here, or you can write it as 5 to the 9 over 2 to the 9. We are not asking you to grab your calculator and find out what is 5 to the 9th. That's not the goal at all. It's the simplified exponential form that we're looking for. All right, here we have an equation on part A, and we have an inequality on part B, and we do have the word solve now that we have equations and inequalities here. So our goal when we're all said and done is to have a value that n is equal to on part A, or less than or greater than or something like that on part B. So we're going to use properties of exponents when possible to do that. And if you notice on the left-hand side of the first one, they are both the same base. So how can I combine 2 to the n and 2 to the 7th? 2 to the, what was it? 7 plus n, or n plus 7, that'll work. And you can write 64 if you want, but it's really not that helpful to write the 64 because I need to somehow compare it to a 2 to a power. So grab your calculator and play with it if you're not sure what the number needs to be. But try 2 to some different powers. Try 2 to the 4th. Try 2 to the 8th. Try 2 to the 12th. Try 2 to the 7th. Whatever. We need 2 to a power so that it equals 64. Did anybody find what it is? What is it? It's not 4th. 2 to the 4th. I think you might have done 4 squared or something. No, you didn't. No, 2 to the 4th. It's not 2 to the 4th. It's 2 to the 6th. Yeah, 2 to the 6th will work. Now here's the deal. Because they're both 2 to a power and they match, the only way that the equation can stay true and equal is if the exponents also match. So please don't go marking out the 2's. We're not canceling them, but we are in fact ignoring them. Now that they match, they're irrelevant. Okay? So now I'm going to actually say, I know now that 7 plus n has to equal 6. Whether you physically solve it at this point or whether you can just look at it and tell me, I don't really care. But what is n? Yeah, it's -1. N is equal to -1. Okay, so we're going to attempt to do the same sort of thing on the next problem. Yes, I realize it's got the less than or equal to. It really doesn't hurt anything. It just means that the symbol at the end will be the same. The left-hand side's pretty simple. I mean, 3 to the n, there's nothing really I can do to that. So it means that on the right-hand side, I'd really like to get it to be 3 to a power as well. Now, the first thing to notice is that the 81's in the denominator. I don't want it in the denominator. I want it right there in the numerator. So the first thing I can probably do is to rewrite it as 81 to the -1. Just move it up. But somebody factor for me. What is 81 when you factor it? 9 and 9. Yeah, there's 3 to the 4th. So over here now, I have 3 to the 4th to the -1. What can I do with the 4 and the -1? Right, multiply them to make it -4. And again, the 3's match, and they both have an exponent, so the 3's become irrelevant. I can now consider only the exponents as being useful information with the same symbol between them. Whatever it was before, it still is now. So the n value is less than or equal to -4, sorry. Negative 1 was the first one. All right. So I always like to do at least one, if not a couple of problems in each section that look maybe a little bit more like the connection kind of problems in your book. So you can see some sort of application or some error analysis or things in class too. So this is an approximate kind of question, a little bit more like your question C. If you were to take a look at this problem and you were to physically have to divide 20 1/3 by 9 7/8, we would all probably cringe inwardly. Maybe outwardly. You might verbally like tell somebody that's not happening or I don't want to do that. That's what my 10 and 11, my son turned 11 today. I can't say the 10-year-olds anymore. That's what my 10 and 11-year-old would do. They would be, I'm not doing that. That's what they would say. So the word approximate is like our new best friend, because approximate means I don't really have to do the problem, right? It means I get around something to nicer numbers. So what would be much nicer to do here instead of the problem that's really being asked in numerical form? Yeah. It would be a lot easier to divide 20 by 10. And if I asked you to divide 20 by 10, you'd all say, sure, no problem. 20 divided by 10 would be 2. So our answer, our approximation, is that this is about 2. So if you then had to go back and actually solve it, that's not the question, and you ended up getting the answer 20, you would know you did something wrong because something weird happened that was unexpected, right? It should be about 2 when you're done. All right, we have 2 more questions left. I think they're similar enough I'd rather do them in the same video, and I can't do both of them right now. So we're going to pick up with examples 9 and 10 next time. We'll also start 6.4 next time, and we'll do the group work from 6.3. So the homework is not assigned yet. You're welcome to start looking over it if you'd like, but it will be assigned on Friday, which means you will have homework over the weekend. And just keeping an eye open for like the future, we do have a test next Friday. Okay, so test is coming up.